All right. Okay. Recording is on. Let's dive in. All right. We're going to talk about inheritance, which is something that was really huge when it first sort of came on the scene. I don't know how many decades ago. And people kind of went crazy for it, and they've sort of backed off of it a little bit, but it's still a really important tool that most modern programming languages have that helps us write less code. So, but you got to think a little bit differently about the problem in order to actually take advantage of it. And it plays directly to our homework 7. So we're going to use inheritance in homework 7 to make your job easier on your homework. So I have done most of the work and you will have to do just a little bit of the work. And so we'll explain how that is. So just quick reminders. So we have our Lab 5. I think everybody's jumped into that. Sorry, I didn't kind of pull these links out of there, but all the links you need are in Canvas now. So these links, you probably just want to go to Canvas for these things because the Program IZ links are there as well. So, but we'll have a little mini exercise on class hierarchy. When people talk about class hierarchy, they're talking about inheritance, and we'll explain what that is. And we will dive into chess big time on Tuesday of next week to start going over hints and example code. And we'll at least have the code for the bishop for you if you haven't implemented it by that time. But I'm going to keep that embargoed for a little bit longer for folks who enjoy the challenge. But you can start looking at your homework 7 and your pawn and maybe your rook and your bishop class if you want after today's lecture. So today we're going to talk about this idea of defining some generic class that has some of the attributes that we might want, but not all of them. And then using that as kind of like the way we might think of our ancestors passing on attributes to us. So a car and a truck and a bicycle might have a lot of common attributes that a vehicle has, but they might add their own, and that adds some extra sort of differentiation. So these are not pointers, as we'll see. They're a whole different kind of structure. So we don't really kind of create a pointer from a vehicle to a car. This is what we call it is a relationship. We say a car is a vehicle and a truck is a vehicle and a bike is a vehicle. So that means they inherit, those classes inherit from that base class. And this is very different from class composition. We'll do a quick review on that, which is how we kind of build up things by cobbling together or gluing together lots of different classes in interesting ways. So we'll look at simple inheritance, and we'll talk about the kind of the gotchas in C++ and the rules around the order of construction and the order of destruction. And that's really what our lab is about today, is just sort of showing you in very simple terms how those things actually build themselves up and break down. We'll talk about a little bit this thing called inheritance mode. It's pretty advanced. It's probably not even something we're going to do a lot with in this class, but I'll try to introduce it as best I can. It's very tricky to kind of explain in an easy to understand way, but I'll show you the syntax and kind of set you up with something you can play around with a little bit on it. And then we'll talk about how these classes add extra features that might not be in their base class. So extending a class is really done by just having that class add something that wasn't maybe there, right, in the previous level of inheritance. And we'll sort of try that out in our exercise for the lab today, okay? So quick overviews. Remember we talked about this idea of like, wouldn't it be cool if we could come up with an instance that kind of had most of the common things in all the board games that we have thought about or worked on, like rock, paper, shears, tic-tac-toe, chess, checkers, right? They all have a score. Maybe there's like certain things like a secret guess that's unique to them. But they all have like a take turn and is win and some common getters and setters. So it'd be really cool if we could sort of come up with a way to come up with a generic game, but we don't want to be sort of restricted by adding things that might actually make our code work really well for chess, for example. So this was just sort of a simplistic view of us kind of coming up with a game description, but it really wasn't probably very general. Okay. And so our constructor arguments, of course, allowed us to configure our game, and those things are passed into the constructor that creates the instance. Now, the other way we could build things up is to sort of just cobble these things together. And this is what we refer to as composition of classes. So here we saw this one a while back. There's a car, it has an engine pointer, right? And so we need to know what an engine is in order to have a pointer, but we can have a pointer to this engine that we will eventually create by instancing the class and hooking up a pointer in some way. And then maybe we have arrays of instances and all that. So this is really about cobbling together things in different ways. And although there's kind of a parent level class, you might say, it's not really, we're not inheriting anything from the car. We're just sort of gluing together all these different parts, okay? Now, so inheritance is different. It's this generic idea that I have this description of a vehicle, and all vehicles, let's say, have an engine, and they all have a method called do drive, which is like just get going, whatever you are, right? So if we inherit from a vehicle class with a new class, we would like to inherit those things that are in the base class that are useful. Okay, so we should all get those two things automatically, an engine and a method that drives. Now, at the moment, all of our vehicles will drive identically the same because they're going to be inheriting the exact same do drive method in this case, and the same thing for the engine. So by default, this inherited class looks pretty similar. It just has a different name, right? So those are our common, or what we would call base class methods or base class attributes, or data members that come with the class, right? So they just flow down from our ancestor. But we can add our own local methods like open hatchback or fold down seats or open the tailgate. And that's really where this idea of inheritance saves us code. We write the common stuff up here in one class, we inherit from it, and we probably don't even really plan on creating an instance of this. It's just so generic, it's like, why bother, right? We're really interested in creating instances of these, but they're sort of connected in this somewhat magical way, as we'll see as we kind of progress through the next couple lectures. So we would say things like the truck derives from the vehicle, or inherits attributes from the vehicle, or is a vehicle. These are typical ways of describing this inheritance. Sometimes I will say a truck class is a child class of the vehicle. It's a little bit murky because sometimes we talked about parents and children in terms of pointers. So I don't mean to confuse you by that, but it seems in the inheritance way, the way we inherit from our ancestors, that there's a child-parent relationship there. So I'll use that from time to time, okay? And the base class for us, or the ancestor class, usually is only one deep, but it doesn't have to be one deep. It can go way, way back. So most modern programming languages that support inheritance allow you to kind of go back quite a few layers. But it's a tricky thing to build up something with a really deep class hierarchy. So this is what we refer to as our class hierarchy. And one of the first things you study if you start look at a large body of code like a game engine or a math library is the first thing you want to know is show me your class hierarchy. What is the highest level object in your class hierarchy so I can kind of understand what I'm dealing with here, okay? So this is a really great design concept. So we could imagine, for example, now a board game that's very generic, and maybe we never actually play this game, but it's got a lot of the logic for printing out the board and taking turns and tracking who the players are, that kind of stuff. And all of that stuff sort of flows down into here, but maybe there's some special stuff depending on the maze game or the tic-tac-toe game, or whether a word is valid or not, that we would decorate in the inherited class. So thinking like this is sort of a different kind of an animal. It's like, okay, well, what's the common stuff and how many different games am I going to end up developing, right? So that's one way to actually think about it. Okay, so there's our common things, right? And by the way, you'll notice that there's another print grid down here, right? So this class, tic-tac-toe, decided to implement its own print grid. Now, there are some constraints with that. If we named it the exact same method, we are overriding, we're not overloading, but we are overriding the base class print grid method. So those two words tend to get confused, understandably. Overloading means we've got lots of same named functions in a single place, like a single class. Overriding, and I'll highlight this for you, in writing here shortly, but overriding means we've replaced a base class method in some derived class, okay? So we'll throw those two words around, but that has effectively replaced that thing, which is pretty cool, okay? So lots of possibilities, sometimes overriding, sometimes just augmenting things and adding them to our class, okay? But the key distinction here is that the exact same return value and argument type of our print grid must match the overriding call, okay? And we'll see why that's so important down the road, okay? So that is a very, very powerful thing, okay? So here's example 3, right? So a creature, an orc, a goblin, and a warg, right? So we might be fleshing out a generic creature in some game that we plan to build, and that creature just kind of lumbers along very slowly, kind of like a chessboard piece, right? Think of the king. The king on the chessboard moves one piece at a time, one square at a time in all directions. So we could start out with a game where all we have are generic creatures, and then as we develop specific derivations, we can specialize their move, right? So now we override the move for a particular creature, and maybe it can run fast, or maybe it can teleport to some other location, or who knows what, right? So the overriding of that allows me to specialize the logic in that for these kind of instances, okay? So that's a powerful capability, and it lets us sort of start out with generic stuff and then slowly add in more and more variation in a game scenario like this, okay? Another example would be a 3D modeler. So let's say we want to have a 3D modeler that models shapes. Well, let's just create a generic shape class. We don't know what the shape is, but maybe we start slowly adding cubes, spheres, tetrahedrons, etc., right? And those things have different capabilities. Maybe they can draw themselves on the screen differently. They may have slightly different constructors. So we'll see how all of that stuff glues together here in a sec when we get into the code, okay? So the nice thing about these overriding methods are we don't really need to know exactly what we're dealing with if we just want to make that thing move, right? So if we know they all have the exact same move, I could just say, hey, give me a pointer to that thing and I'll make it move. And I don't really need to know what kind of thing it is because we've enforced using the exact same overriding sort of function signature, okay? So there are situations in code that can really get much cleaner where we don't have to say, if I'm an orc, call this, else if I'm a goblin, call that. We just say, hey, go move that thing, because we know they all have an overriding move that matches across all of them. So goals of all this save us from writing extra code, right? We don't want to write the same move stuff if all these things are moving the same way, right? There's probably going to be fewer bugs. We kind of don't have to study all of the code at once. Once we finish the base class, we just put that away and we focus on the specialization. So in chess, when we think about moving a pawn, we're really just going to be thinking about whether it's legal to move a pawn from one location to another. That's really our main consideration with a pawn or a bishop. It's like, is it legal to move a bishop from this place to this place? If it is, I'll take care of the rest. You just tell me if that's a legal move. So that's a lot simpler problem than how do I make a pawn move in a chess game, right? Including check and all that other stuff, okay? So we can think of our design high level, right? And how we want to solve and tackle our problems by sort of designing our class hierarchy in a specific way, okay? The limitations of this is sometimes there's a lot more digging to figure out, hey, where is that attribute defined? I don't see that in my pawn. Like my pawn doesn't seem to have a row or a column. Oh, well, it belongs to the base class for the piece, right? It's not in the pawn, right? So we might have to go hunting through the hierarchy to find a particular attribute, which can be a little annoying. It also means if we don't get our base class correct, and we got to change it later on, it's going to break everybody's code. Like everybody who's working on chess, if we were a part of a large team, changing the base class is a very terrifying thing. So you tend to be really careful about what you put in your base class, okay? Because it sort of just makes things more complicated, okay? And sometimes you don't really need to go crazy. So this is what a lot of people did in the beginning. They were like, hey, I'm going to make a 4-level hierarchy. And they ran into all these problems. And, other folks came along and said, why not just like have one class and just have like a different name for orc, goblin or something, right? Do they really need to move differently, or can we just set some variables differently in their data members? So there are situations where we really don't need to do that. Okay. Or maybe cobbling things together with composition would be better. Okay. So it's really powerful, but it is potentially complex. Okay. So let's take a look at the code for how we do this. So we're going to use our foo and foo junior, silly names, but they could be anything. Our base class is going to be foo, and it's going to have a data member called val, and it's going to be just like that, right? Like we've always done. So it's got a public data member for now. It's got a constructor initializer list where we're just going to always put a 10 in there, okay? So it's kind of silly, but when you call the default constructor, I'm just going to shove a 10 automatically in the data member for that class, okay? So I can instance it this way, which we've done many times, right? No parentheses there. So val will be a 10 in that case, okay? Now, if I want to derive from foo, all I got to do is just put this kind of secret colon public foo in there. So that's basically says, that's my ancestor. I am from foo, right? But my class name is called foo junior. So if I only do that, and this is called the inheritance mode, notice it's different than this public here. It lives kind of between the curly brace and the class name, right? So it's kind of living in this spot right here. So we're saying, hey, I am inheriting publicly from foo. We'll talk about what that means. And that means I automatically have that attribute, okay? So we say we derive publicly. So if I just do a foo junior and I say, hey, what's my value attribute? It's going to print it out for me as if it was in the junior class. So that's what it means, of course, to inherit these attributes or these data members, okay? So we really are kind of, as foo junior, including a copy of a constructed foo instance. So it's actually there with us in the box, so to speak, of the foo junior instance. And that's how foo junior sort of manages to know what it has in its base class, okay? But we can refer to it as if it's right there inside of the junior class, okay? So all pretty simple so far, kind of makes sense, right? Both of those things can be accessed, directly through the instance, okay? So now, but how do we call our constructors? This is where things get a little specialized. So here's our foo class again. I've kind of, made it, given it a defaulted value, right? B for base class, base value. So the base value is going to go into the data member for the class. So that's how it could create the base class, okay? So that's me just doing that. Now, if foo junior is going to derive from this, how do I control the val through the foo junior constructor? So, and again, notice there's a public up here that says, how do I derive from this foo, right? And then there's the public down here to talk about the things that are part of foo junior, okay? So that's my constructor. And I could do this. I could say, okay, you gave me a FV for Foo Junior, and I am going to just shove that into my inherited attribute. And that's okay. It's not wrong, but it's essentially going to, only do it in our constructor. Okay. So we've sort of got around our base class. Okay. So it's not ideal, but it works. And it only works because we have a default constructor for our base class. And I'll show you why that is so critical. Okay. So we construct Foo Junior, it has to be able to construct this first, and then it can assign members that come from the parent. Okay. So that means this has to be a default constructor. It has to be able to be created without us telling it what to do, because you can see I didn't give any instructions to my base class here. Okay. So let's just sort of see if we can figure out why this one's not working, right? Because this is one of the first things we trip over when we start doing these inherited things. We're like, okay, everything's going well. I'm doing it just like we did in class. So why isn't it compiling? So let's see if I can kind of elicit this piece of insight here. So we try to run this thing. Everything looks pretty good. I got foo, right? Here's my foo class. All right, so there's my foo class, there's my foo constructor. I get an X, I assign it to my X thing. And then I go down here and I try to do what it looks like we did in class, but it's not going to let me do it, right? It's not going to let me create that. It says constructor silently calls foo by default. Oh, that's my note. It's saying no matching constructor for call to the base class. Well, what does that mean? What it's telling me is it's trying to call the base class automatically before it can do this. But the base class needs an argument. So if I want to fix it, I have to turn this into a default constructor. So I'll just give it a 15 for no good reason, right? So that's going to make it happy, right? So now we can construct Foo Junior because Foo gets constructed first. So notice the order of the messages that print out. The Foo constructor triggers first over here, right? So it is being silently called right here, even before we are allowed to activate anything inside of Foo Junior, okay? So that's an important thing. Base, then derived class. That's the order in which we're going to sort of evaluate that stuff. Okay. So you can kind of see, that sort of manifested in our code. Okay. So that's good rule of thumb number one. Always make sure all of your base classes or ancestor classes have default constructors. Okay. So that is going to really help you there. Okay. And so this is essentially has to call foo. It has no choice. It happens silently. Okay. So let's try a different one. So here is a base class creature. All creatures have weight. So we're going to give ourselves a default constructor where we pass the weight in to our creature. Okay. So if we were creating a creature, that would be pretty straightforward. Okay. And there's our default value. Okay. And if you forget that, it's really painful because the compiler bugs are kind of not very helpful. So let's derive from our creature and make our goblin. And we'll use the public inheritance mode. So goblin derives publicly. We'll talk about what that means here shortly. Okay. We got to have that. If you leave that out, it's not going to work properly. So that's really another area where in chess, possibly, people might forget that. So keep that in mind. But here's our goblin constructor. So somebody gives us the goblin weight. So how do we get that weight into the base class weight attribute? We could do it this way. We saw that previously. So we're just sort of default constructing the creature and then coming back and overriding its weight with our passed in argument there. So that's okay, but it's going to happen after the creature base class gets constructed. Okay, so let's just try to do that step one. And let's create the goblin class. Let's derive publicly. Let's create the orc class. So a little bit of iteration here, a repetition to just strengthen our understanding of that. And then see if we can create these things and give them weight. Okay. and then see what happens if you try to create an instance of the base class directly. Okay, so let's see if we got this one up and running. Okay, there we go. So we've got our base class. So let's create a goblin class, goblin. Okay, colon public creature. Okay, and then we'll give ourselves this, and always a semicolon. And then we will, what do we want to implement? Goblin creature, give a goblin integer weight argument for the constructor, right? So we need our constructor, goblin, right? Int, and we'll call it GW, okay, like so. And we will use our constructor to change the weight to GW, okay, like so. So that should work. Let's see if that compiles at least. See if I haven't gotten any problems. Okay, good. So that's good. Let's just replicate that and make our orc real quick. Okay. Same kind of thing. Orc. Okay. All right. So there's our, and we'll call that our orc weight. Not that it really matters. Okay. And then we'll create an instance of the goblin. So goblin G. Okay. And we'll make it a 10-pound goblin. And then we'll have orc O 15 pounds. Okay. Okay. And now we should be able to print this out. So let's just test what we have so far. Okay, goblin G, create an instance. Goblin int is private. So I did the thing that I always say not to do, and that's I forgot to make it public. Okay. It's by default, classes make their data members and methods private. So I got to make it public. Okay. So let's try that again. There we go. Okay. So, and we can finish that out, right? So we'll just say, okay, see out, the goblin is this, right? And the orc weighs that, okay? And that's the base class inherited method, of course, okay? Okay. So that is us doing it kind of through the, whoops, and you can go on and on with this, of course, but doing it through overriding of the base class, okay? Like so. Relatively straightforward. Okay. And forgetting the public obviously is a problem. Just demonstrated that very clearly, right? It stops us from being able to, inherit that stuff. Oh, we did it in the constructor, but if we did forget it here as well, right? If we just said that, right? Think we'll have a problem, right? Yeah. It's like, hey, this is not accessible because the derivation falls back to being private, okay? So we got to have that public too, okay? And we can actually create a creature if we want to, right? It's a blueprint, and for the moment, it is a viable instanceable class. So we could have created a creature instance if we wanted to. It might not have been useful for anything, but we could have actually done that, okay? And we'll see that in next week, we'll learn how to prevent that from happening by something called an abstract class. So we can make the base uninstanceable so that it's only ever possible to use it as a blueprint and not as something that kind of leaks into your code. Okay, so that is called an abstract class, and we'll talk a little bit about that next week. Okay, but let's take a look at a better way to initialize base class attributes, and this plays directly to your lab for today. So we've seen that the base class gets constructed first, okay? So Foo Jr. is going to call that constructor with default arguments unless you find a way to specify the arguments, okay? So here's us doing that, right? And it is tempting, right? So there's our base class. Here's our derived constructor, and I've kind of just used my constructor initializer list here, right, to initialize the y, right? So I'm initializing this y with the value that's passed into my Foo Jr. constructor, and I'm letting the default value initialize the x, which is kind of useless. I didn't really have any specific stuff that I wanted to do to the x there, okay? So we've seen that, we can do that. Now, it's very tempting, and many of us will make this mistake. Notice that I left a little gap here. Hey, what if we want to just decide what x is right here? What if we try to do that? So it's tempting to try to do that, right? Because you think, oh, okay, that's my x. But it turns out that the foo class has not been constructed yet. So we cannot use the constructor initializer list to do that, okay? So that's going to cause a problem. You might think, well, that's pretty limiting, but there's a better solution. So what we want to do is instead just call the base class constructor right there. We'll just call it. We'll just say, hey, foo, here's your x, right? So we cannot do any individual members, but we can call the actual constructor. Now, this is something we've seen we can do. We just did this, right? But it kind of doesn't work if I want to initialize a constant value, which doesn't happen all the time. So this is sometimes an okay solution, okay? But we're still going to end up calling this first and then overriding it later. So the better way is just to sort of call the base constructor this way, right? So here's my base class, right? Here, constructor, and here's my foo junior constructor. Sorry, this is calling the default constructor, sorry. And this is an updated version that calls the base class constructor and then assigns the y value, okay? So this is really the more powerful and sort of canonical way to actually reach into your base class. So if you're a lab today, if you want to initialize your parent class, you are going to call the parent constructor, okay? And if that parent constructor needs to call some previous ancestor, it will call that ancestor's base class, okay? So in your chess game, when you are initializing or constructing the pawn, you need to call the constructor for its base class and tell the base class where that pawn should be on the board. And you'll see that in the code, but it just sort of tie in there for the homework that you'll be looking at, okay? And that's okay. That's really the cleaner way to do it, okay? You just call that constructor and then we'll take care of the rest later, okay? So here that code is kind of laid out, right? So that's what's happening. So what happens is when we stack up these classes, it's construct, then construct, and if there's more classes, they construct. But we have to pass things kind of up the chain, right? So I'm going to pass you something, and you might need to pass that to somebody else. And then the construction happens kind of from the top down. Whoops. Okay. So it's like base down, like so. Okay. So let's see if we can do a little coding with that to demonstrate how that works. Okay, so we got our creature and our goblin. We got a 10-pound creature by default, and we want to create a 20-pound goblin with 12 legs and print its weight using the base class method. So I put my base class things kind of in yellow here, even though that's a little bit of an overuse of my colors. And then we'll modify the initialization list to use the base class to pass the weight down, okay? And we can verify in main that that thing got initialized properly. So let's try that real quick. Okay. So here's our creature, right? Defaults to W, okay? And here's our public derivation from creature. And we're going to add legs to our class, right? So we only had weight up here. So we're adding some legs and we're trying to initialize our legs, but we like to also call creature. So let's say creature, and we're going to pass in the weight, right? Even though that weight was, of course, passed to the goblin constructor, we're going to pass it on up the chain to the creature, which will receive it and construct, so it becomes underscore W, right, for the creature. And then we can continue on, right? And here, we're kind of already done. We've initialized everything, including the legs, so we're just sort of documenting what just happened. We don't really have any work to do inside of our goblin constructor anymore. We've got it all handled there, okay? So down in main, let's create a creature. So we'll just say creature C. We'll give it 10 pounds. Okay. That's our base class, right? So we're just testing out that that way works. Okay. And then we'll say C dot, what do we call it? Print weight or print weight. Yeah. C dot print weight. WEIGHT. Okay. Okay. So let's see if that works. Okay. So my creature weighs 10 pounds. Now let's create a goblin. So we'll say goblin. Yeah. Goblin G, 20 pounds, 12 legs. So I think that's the right order. Let's check. Instructor, goblin, weight, legs. Okay. So one of them is going to travel to the base class, and one of them is going to just go directly into the goblin class. Okay. So we'll say G dot weight. Okay. And oh, right. So that's our print weight method, right? But let's do it going directly for the member, just to remind ourselves we can do that, right? WEIGHT. Okay. Oh, sorry, C out. C out. WEIGHT. Okay. Yeah. Okay. I think that is all I need to do. Let's see if we get that. Yep. So 20 and 20 and 20, right? So there's my direct access to the base class weight, and here's us calling the base class method, okay? And we're doing it through the goblin, which is the derived class, okay? Pretty straightforward so far, okay? So there's our derived class. So obviously, if you were only just trying to create a goblin, all of this extra work is probably unnecessary. But if you're planning on creating a whole bunch of creatures that share a lot of common traits, then you're going to save yourself a lot of time, which is pretty cool. Okay. Okay. And key things, I think we probably covered these guys, but yeah, I think we touched on that. Questions so far? We pause there momentarily. Okay. All right. So let's talk a little bit again about constructor order. So our lab today is just trying to make things a little more complicated. You have 4 levels in our hierarchy in the lab today. So here's just 3. We're calling them A, B, and C. But again, we got to construct base class toward the most derived child. So that's the order in which the hierarchy needs to construct itself. So if I say C, my C, that instance of my C is going to have a copy of B and A in the box with it, okay? So it's going to kind of cascade all the way up to the A and construct in the downward order there, okay? So base to child, okay? And so these are non-static, right? Last week we talked about things staying in the factory. Well, these are in the box with the instance. So every instance of a derived class in C++ has all of the ancestor classes traveling along with it. Okay? So our order calls the B constructor, which calls the A constructor, and then A constructs itself. Then B constructs itself, and then C constructs itself, okay? Perhaps obvious. Sometimes people will try to skip a level, and they'll say, oh, I don't need to do anything in B, so I'll just sort of call the A constructor. Not allowed to do that. So C has to trigger the B constructor either automatically or explicitly. So trying to bypass a level will not work for us. We'll get a compiler error on that. So there's our constructor order, okay? Destructor order, as you might guess, is in the opposite direction. So when my C goes out of scope, it's got to clean itself up in the reverse order of how it was created. So C gets called first, and once C is destroyed, then B gets called, and then A gets called, which is kind of cool and mostly makes sense, I think probably most of the time. If you create some dynamic memory in A, and then maybe you depend on that in B, and then maybe you depend on that in C, you kind of need to destruct in the reverse order, okay? So we'll see that in our lab today, if you document your destructor, if you put a little message in there, you'll see that calling order kind of reinformed or re shown to you, basically. Okay, so those are kind of the basics. Not that complicated, but when we start putting code, out, it gets a little bit tied up together. It seems a little confusing. But that's kind of our lab today. So let me then go into one more topic here before we try some more examples. This one is my least favorite topic to talk about because it's just very difficult to explain. So bear with me while I attempt to talk about this special inheritance mode. So inheritance mode, again, is we've looked at it as being public. It's like, hey, I would like to inherit from my ancestors in a public way. So what that says is that my members and my methods can be accessed from anywhere, including outside of the class. Okay. This is just, sorry, this is an inheritance. This is our just basic access for members, right? So we know about this. We haven't done too much with protected, but protected basically means, hey, my members are not accessible. They're kind of private unless you're a derived class. So protected is kind of like all in the family. It's like nobody else gets to have access to my members except people who are in my class hierarchy. So that's what protected means. It's like if somebody inherits my protected member, like a data member or a method, that's okay. They can use it, but they can't. It's not accessible to the public. And then, of course, private is like nobody, not even, people in the family get to access it. Okay. So here is our basic access members, right? And we've seen all this. We just haven't really done a lot with protected because protected doesn't affect anybody in any interesting way until we start doing inheritance. Okay. So when we derive, that'll change the behavior a little bit. Okay. So let's take a look at how this might crop up. Okay. So here is where that goes. We've got our base class and the child, it's kind of weird. The child gets to decide the rules under which this information is going to flow downward, which is kind of weird. You'd think it would be the parent that would decide, but in C++, the child gets to decide how these things will be inherited. And so that's going to be public, which means whatever the visibility was in the base class is going to be preserved if this is public, right? Okay, and this is most common. This is what we were just doing. If it's protected, that means that anything that is available to us sort of allows public and protected base members of this class to be accessible inside of the child, but they are not accessible through any derived class interface. So that means they can't be passed on to anyone else. We've stopped the chain of inheritance below us, okay? Which is kind of weird, okay? So that's the hard one to describe. And then private just shuts off all access. This makes inherited members private, and it's, of course, not visible outside of this class, okay? Subtle. We're not going to do a lot of testing for you on this, but it's important to know that this does exist and it is different than the functionality we see in these kind of access modes. It all has to do with the inheritance, passing attributes down the line. Okay? So think of it as keeping it in the family. That's been the easiest catchword that I've been able to find. Okay. I am not going to go through this because every time I do, I finish and I feel like it just goes over like a lead balloon. Since we're not really testing on this, I'm not going to kind of torture you with it. But if you are really, really interested in how this works, you can either study this or you can try an example where you just change the inheritance mode and see what works and what doesn't work. Okay. But I'm going to kind of stay away from this for now. Okay, because we got a lot of other material we still want to cover. Okay. Again, though, protected base class members, of a base class are not accessible in an object or instance only within derived class, right? So we can't access them outside of the class, only from within derived classes, okay? And those same members are accessible inside the derived class, regardless of the inheritance mode, right? So they'll always be accessible inside of our class, okay? So I'm going to stop right there and I'll show you this code. If you want to poke around in this and see what you can access, you're welcome to kind of do that. But I think it's just a bridge too far for what we're going to do in this class. Most of what we're going to do is going to be using public here. Okay. I think that's all I'm going to say about that. Okay. Let me see if we've got anything else. Yeah, that's it. That's all I'm gonna say on that. But that is called inheritance mode, sometimes derivation access, if you want to search that up on the internet. Okay. Okay. All right. Let's talk about kind of modifying our classes, like adding a tailgate to our truck, right? Because trucks are different than our base class. So it's pretty easy to do that if we have permission in the derivation, right? So we can add stuff like legs to our derived classes. I think everybody probably gets that. We can also, as we'll see, change the base class privacy of getters and setters, or methods. We can use getters and setters in a derived class to expose private information that comes from our base class. So we have a lot of power in our derived classes. So here's that happening, right? We've got a protected member X. It's not public. We're keeping it in the family, but we have a rogue ancestor here that has decided to release it through a method. Just say return X, right, in the getX method. Perfectly legal. The ancestor actually has the right to do that, even though that this is protected. Okay, so that's one way we can reveal X, okay? So even though it's sort of essentially private to the outside world, okay? So we cannot do this, of course. We can't say jfr.x, but we can say jfr.getx. So it's almost as if it was private, which is what protected really means, okay? Now, if this was private over here, then we would not be able to do this, okay? So that's the difference between making this protected in the base class and making it private, okay? So that maybe helps explain a little bit what this whole process means. Okay. Now, shadowing is one word I use to describe sometimes the accidental process of creating the same named variable in one place that exists somewhere else, okay? We've often done that in methods where we kind of accidentally create a data member in a method when it already exists in our class. This is similar. I have an X in my base class, and now I've created an X in my ancestor class. And so when we do a return X, which one are we talking about here? Okay, so C++ typically works local first. So it's really, it's going to be returning this one right here, okay? Which may not be what you intended, right? So a lot of people accidentally shadow their base class methods, and we don't really normally want to do that. That's not really something that makes a lot of sense on the surface, okay? Not for data members anyway, okay? So you might be interested to know that we can be very specific about which data member we're talking about, though, by prefixing it with our good old scope resolution modifier. So foo junior :x very clearly says we're talking about this. Foo :x sort of means we're talking about this, okay? So when we're returning something, we could say return base class X versus this X, okay? So this is the child's X, but we could have said foo :x if we really, really wanted to. Kind of silly to to cause yourself so much risk by naming those two things the same, but that's one way to be highly specific about where that thing is coming from. Okay. So here's that. You can say return arrow X, regular X, foo junior X, which is in the derived class, or foo X. And I think I've seen some folks using this already, in fact, probably something you might have picked up somewhere on the web in some good example code. So that's totally okay, right? Um, so interestingly, we can even do it like this. I can say cout foo junior X, which prints the child's public X. I could even say, this is really surprising, JFR foo junior derived class X is the same. Or if it wasn't private, I could say base class X. Okay, so I can put that qualifier in front of any data member name if there's some ambiguity, and it will help the compiler know what we're talking about. Okay. So we're not going to run into that too often, but it's just good to know that is there. Okay. Now that's shadowing of the data members. Not very useful, but when we talk about overriding, which we kind of introduced in the beginning, that's when we're overshadowing methods. So this method is overriding that method. Okay. They both have the same name and the same function signature, integer, integer, no arguments, same name. So we would say that getX is overriding getX in the base class. And sometimes that is a useful thing to do, okay? So, but that's how we would actually do that, right? So that is called override, okay? And it has some useful things. So I can say foo junior.getX, and it will default to the child's derived getX method, okay? If I explicitly call the base class method, it will bypass the child's method and go get the base class one. Because remember, both of those instances are in the box together. So we can always reach into the base class that way if we wanted to. But usually we want to fall back or fall down to the most derived method. That's the overriding feature working for us there, okay? So, and this is how chess, again, is going to work for us. A pawn is going to have an is legal move. Queen is going to have an is legal move. The base class is going to have an is legal move. But we want to fall through to the queen's base is legal move if we're calling on the queen, okay? And we want that to just sort of be automatic, okay? So again, we could use the foo, double colon to get there, right? There's a few, there's a few gotchas in here. We could end up in an infinite loop if we're not careful, right? So we end up calling ourselves, even though we think we're calling the base class. So we got to watch out for that, okay? But we could use those access qualifiers or that scope resolution modifier in main as well. Okay. Oops. So we're going to use that to our advantage, right? Overriding. Okay. And it's it's super powerful, especially since sometimes, as I mentioned, we don't know what kind of instance we're looking at. Is it a queen or is it a pawn? Like all we have is a pointer. So how do we know what kind of thing we're pointing to? Well, C++ will figure it out for us, which is what we're going to see mostly next week. But that's the reason all of our is legal methods or our move methods have to have the same function signature, because we don't necessarily always know what kind of derived class we're dealing with. Okay. So good and powerful stuff. We'll kind of dig into that mostly next week. Okay. Okay, so let's try just a couple more modifications to this. I think we'll get you out of here before 7. But here's our creature class, right? And so we've got our print weight, and we're going to have a generic move. So let's look at this overriding, and I think this will be our last practice problem maybe. So we've got a base class method for moving our creature around in a very generic way. And so if I created a creature and I call the move, I'd see that method there, okay? and we've got our weight. Okay. So here's our goblin, and we're going to write an overridden or override base move method that replaces the creatures, and we'll have it say something like the goblin is moving, just so we can kind of tell the difference between those two things. So let's do that real quick and see that working in action. It's kind of nice to see that it actually works. Okay, so here's our base class. It's got its creature move, right? Here's our goblin. So let's write the move method. It has to match this function signature. So let's just start there. Bring it down, paste it in, okay? And we'll say goblin, right? Goblin is moving. Okay. That, okay? So down here, I create a goblin, okay? And we're going to call the move method. Okay, so we're going to say g dot move. Let's do it with that particular instance. So g dot move. Okay, okay, and I think we will see the goblin is moving generically. Okay, creature's moving generically, goblin's moving generically. Let's see why that's doing that. Let's comment this out for a moment, just to highlight this one thing. So goblin is moving generically. Why is my goblin moving generically? Here's my move inside of my, oh, because I didn't change it. Goblin is moving like a goblin. I'm sorry, goblin. Okay, okay, so that's working just fine. Okay, so some important last few things here for you. So let's do this thing a little differently here. So I'm going to create a pointer to a goblin, okay? And we've done this. So I'm going to use the pointer to move the goblin, okay? So I have a 20-pound goblin with 2 legs moving, okay? So I should see 2 goblin moves, okay? So here's my moving like a goblin, and here is my, where'd my other moving like a goblin go? All right, okay. G pointer move. Oh, right, of course. So we are not, right, of course, we are not, it's not working, right? We're calling our base class method, okay? So same thing over here, okay? If I do that again, it's like, why isn't this working? So we're gonna cover this in just a second. It should be calling our derived method, but it's still calling our generic method, okay? So we want to force that base method to work, right? So let's just kind of look at this real quick. So we got it working for an instance, but not for a pointer. So pointers seem to not be working for us, okay? That is kind of one of the key things, okay? So we're going to have to figure out how to get it to move in the pointer situation, which we have not talked about yet. Okay, so that's a problem that we're going to tackle, that part right there with the pointers, next week. Okay, so we have not learned everything we need to learn how to make this thing use a pointer to figure out actually how to move. Except that, notice, now I'm picking up on my own notes here. This is a creature pointer, and this is a goblin pointer. Notice that both pointers are compatible. So this is one thing we're going to dig into, is that C++ will let you create a base class pointer to a derived class instance, okay? So in this case, it's triggering the base class move, and in this case, it's triggering the goblin move. I believe that's what we actually saw. Creature's moving generically, or I got that backwards. Goblin is moving like a goblin. Goblin is moving generically. In any case, we'll come back and we'll talk about what we've got to do to get this stuff to work so that we can get it to work with any kind of pointer and do the right thing, which is what we want our chess doing as well, okay? So kind of mangled that a little bit. But this is where we're going to go next week. So for now, let's just kind of quickly highlight our lab and get you guys on to the next thing. So what we want to do in lab 26 is create a cascade of classes: grandparent, parent, child, grandchild, okay? And each of these is going to add a unique attribute, A, B, C, D. So each class should add that attribute, okay? And essentially, the most descended instance will have all those attributes, okay? And we need a default constructor for each one of these, just like we were doing in class. And let's just, for the sake of debugging, make it simple. 1, 2, 3, right? So we can kind of tell they all are properly initialized, okay? So a default constructor for that. And then just print out a message so you can see every time that the constructor is called, and print out the value in the constructor of all of the attributes that it's inherited, okay? So grandparent should print A, parent should print AB, child should print ABC, etc., like that, okay? And then just add a message to your destructor to help document how these things are kind of unwinding, okay? And all you got to do is create an instance of a grandchild. That's all. We don't want to create every one of these. We just want to create one and then see how it triggers these constructors and destructors, okay? And check your output to make sure everything makes sense to you, okay? And I think that is it, right? So let me just take a quick look. There's not a lot of code given to you here, but you should be able to throw this stuff together pretty quickly, okay? So just create your classes. Oh, there's some of it here. So you'll need to just finish the child and the grandchild, okay? And there's us creating the grandchild, okay? So I'll leave you guys with that. And next week will be all about chess and inherited classes. Okay. Thank you. I think that's all. Oh, yeah. And this is what your output should look like. Okay. So I'll leave that up for you. Okay. Thanks, everybody. Have a good weekend.